Hello everyone. Today we will work on this section 14.2. It is on limits and continuity. Now before I start this going over problems from this section, I want to go over some important part first. Okay. Of course, what I said here is the general sense, not in strange cases, but we know that from calculus 1, we know that all polynomials are continuous everywhere. On all real numbers, right? Okay, now of course, then if we extend this to multivariable polynomials, then it will also continuous on the whole planes. Okay. As for rational functions, oh, actually one more. Beside polynomials, we also have exponential. Okay, and exponential functions. Okay, now rational functions and logarithmic functions are continuous on their domains. Okay, I think for now I prefer to say continuous on the boundary on the interior of their domains, interior of their domains. I need to explain a bit about that though, but I will leave it later. Now, why do I mention about continuity first, while in our textbook we talk about limits first, then continuity? Because I basically want to borrow the idea that if a function is continuous at a certain point, if fx is continuous at x equals to a, then the limit exists, right? Limit of x approaching a of that function exists. Okay, of course, I said earlier I borrow because continuity is actually a much stronger case compared to just the existence of limits. In other words, it is possible we have a function that is discontinuous at x equals to a, yet the limit still exists. Okay, we can easily get that in calculus 1, a function that looks like this. Right, the limit exists, but it's not continuous. Okay, but once it is continuous, then the limit exists. That's what I'm saying. Okay, once it is continuous, the limit exists. Now that's in calculus 1. The notion is being carried through in calculus 2. Okay, now then we will see the issue at hand. The issue is what if we try to find the limit, or we try to find the limit when xy approaching a coordinate, and this coordinate is actually in the boundary. of the domain. And that boundary is not in the domain. Some example in calculus 1. Okay, let's say we have fx equals to natural log of x. Now the domain here is all positive real numbers, right? From 0 to infinity, not including 0. So the similar issue that we are talking about will be when we have limit x going to 0. Okay, now notice that 0 is at the boundary of the domain, but not in the domain. Okay, so we are talking about those kind of cases. Now, so if we step back a little bit, what if then we are trying to find the limit of a function where the xy is approaching a coordinate which is in the domain? Then we just plug in numbers. Okay, we just plug in numbers. For example, if we take a look on number, I think we can do number 7, right? Number 7, okay, limit xy going to 2, 1, 4 minus xy over x squared plus 3y squared. Okay, and you know that 2, 1 is in the domain of this function, right? We just plug in numbers then. That is 4 minus 2, that's 2 over 4 plus 3, 7, right? Okay, actually the issue for this number 7 is what happens if the limit approaches 0, 0. Okay, which I will discuss later on. Okay, but let's table that for now. What if the question were limit xy going to 0, 0 of 4 minus xy over x squared plus 3y squared. Now you can see the domain of this function is all real numbers except origin, right? So the coordinate origin is not in the domain, but it is at the boundary of the domain, right? And then it becomes the issue, right? Okay, now we will take care of this later on. We take care of this later. Okay, but for now, if the coordinate it is approaching to is in the interior of the domain, like number 7, then we just plug that number in. Okay, you will see that's the same case with number 8. Okay, now let's go on. What if it is in the boundary of the domain? And we start thinking, right? So for example, number 9, limit xy going to 0, 0 of x to the 4th minus 4y squared over x squared plus 2y squared. Now, one of the basic technique we learned in Calc 1, which we still carry through here, is to try to factor. Okay, if we can factor, we try to factor and see if it works well. Now, in this case, I can factor the numerator. We get x squared plus 2y x squared plus 2y, and then x squared minus 2y over x squared plus 2y squared. Seems like it doesn't work, huh? If only that were 4y to the 4th, then it will work very well, huh? Okay, but seems like we cannot cancel this. So what do we do? Interesting, huh? Okay, but you see that if this were a 4, the exponent here were 4, then this will be 2y squared, and something cancels, and you have a good result, right? Then the result will be the limit is going to 0, the limit exists. Okay, but what happened now? It is not. Does the limit exist? Okay, so we now come up with the issue. Maybe we again we step back a little bit. If the limit exists according to the plan, if the limit exists, then we use squeeze theorem. Of course, this is not the only technique though. Okay, and I think I have found very rare cases where my squeeze theorem doesn't work, but still the limit exists. Okay, but if the limit does not exist, then we show 2 different paths with different limits. Okay, if we know the limit exists, or if we know the limit does not exist. Now you can see that I start this section here not with a full confidence in doing my stuff. No, it's not that I don't have confidence. I think I prefer to say that I myself encountered, I remember years ago, I think in 2007 or 2008, or maybe 2009, one of my summer class at East LA College, one student asked me that question. Thomas, I know what to know. If the limit exists, then we can show that by squeezing it, right? If the limit does not exist, then I show 2 different paths with different limits. But how do we know the limit exists or does not exist to start with? And that question makes me, my answer at that time I remember was very disappointing. And I say, oh, by instinct. You just know it. Okay, and right after I say that, I said I was not happy with my own answer to that student because it's way too non-scientific, right? Way too intuitive. It's my job to teach them, just like it's my job to teach you now. Okay, and because of that answer, I said it's by instinct. Okay, and then I look at that students. I remember I say, I'm sorry, that's the best answer I can give you right now. You know, but I promise you I will look for a better answer than just by saying by instinct. Okay, then I looked through a lot of textbooks. Trust me, actually, since that night. That class ended at I think ended at 10 o'clock at night, so the library is closed. Okay, I have some calculus textbook at home, so I gathered all my textbooks and then I looked for the answer for those questions from those books. No textbook actually give me the hints. No textbook actually explain how do we know that the limit exists or not. Okay, and I think as far as I remember, no textbook even give us a hint on how do we find out. So I was really thinking hard on those days. I remember it took me 2 days to give that student a more systematic and structured answer. Okay, and my answer to him, fortunately, actually satisfactory to him. He said, Thomas, I see what you try to say, right? because it was summer. It was summer class. So the next day I met him again. I said I start having some hints on how I will approach that kind of question. Like if I have a limit question, how do I know if the limit exists or not? But it's not well structured yet. Give me another 1 day. Okay. So the next day I came up to him, and then in fact I also explained for the rest of the class that this is what I think I will do. So you will see my me going over problems from this section today is basically the reflection of what I will do on my scratch paper, and then what I will do when I show the work. Okay, now let me start by doing the following. Okay, I will show my work on the left hand side, my formal work on the left hand side, but my scratch work I will do it on my right hand side. And that's not what you show to on your paper, okay? I mean, of course, on my paper you can, but you still separate that as your scratch work, okay? Now, the idea is, if the limit exists, then we can squeeze them, okay? Now, if the limit does not exist, then the squeeze will fail. The squeeze will fail at some path or on some paths if the limit does not exist. Okay, so we try to squeeze that limit. If the limit works, I mean the limit exists, then the squeeze will work. If the limit does not exist, then you will find some path where it doesn't work. Okay, now let's start with this question number 9 here. Okay, you will see the following. Okay, let me erase this first. Let me go ahead with the answer, and I will show you later on why I have that answer. I will say, well, I will say that the limit does not exist along x-axis, which means my y is equals to 0. Okay, my x is approaching 0. Okay, you can say that we have along x-axis. Okay, we approach the origin along x-axis, okay, which means we can also parameterize that path using x comma 0 going to 0 0. Okay, so limit xy going to 0 0 of x to the 4th minus 4y squared over x squared plus 2y squared along this x-axis. You will have limit x going to 0. Maybe I write it this way first. X comma 0 going to 0 0 of x to the 4th minus 4 times 0 squared over x squared plus 2 times 0 squared. That is limit x going to 0 of x to the 4th over x squared. Okay, yes, x to the 4th divided by x squared is x squared, and it is equals to 0 when you replace the x by 0. But those are 2 steps though. Okay, we need to show those 2 steps. First, we need to simplify first, and the simplification is possible because x is approaching 0 but not 0. Okay, then at this point you plug in replacing x by 0, and therefore the limit notation disappear. You get that 0. Okay, that's if we go along x-axis. However, if I go along y-axis, which means I set my x equals to 0, but my y is approaching 0, we will get, in other words, we are using y comma 0 approaching 0, 0. I'm sorry, 0 comma y. I'm sorry, 0 comma y approaching 0, 0. So limit xy going to 0, 0 of x to the fourth minus 4y squared over x squared plus 2y squared. That is limit 0y going to 0, 0 of 0 to the fourth minus 4y squared over 0 squared plus 2y squared. That is limit y going to 0 of negative 4y squared over 2y squared. That is, notice that I will still need to write the limit. Why? Because what I did there is I'm canceling the y squared, but I'm not applying y equals to 0 yet. Okay, this is then equals to negative 2. Okay, so the conclusion, so the limit, because it gives us two different limits, right? Using two different paths, so x to the fourth minus 2y squared over x to the x squared plus, I'm sorry, this is 4y squared. And this is 2y squared, does not exist. You see, those are two different paths that give us two different limits, and therefore the limit does not exist. Okay, now we come back and ask ourselves, Thomas, how do you know to start with that the limit does not exist? And if the limit does not exist, how do you find those two paths? And my answer is going back to your scratch paper. This is my scratch. Let me use red color, my scratch work. Okay, so I'm supposed to do this scratch work first. Okay, but I hope along with once you do some exercise, you stare at that limit question first, of course, and you to think of some simple paths like along x-axis, along y-axis paths. Usually that gives you the idea already, right? Okay, without doing scratch work. But if you want a more systematic approach to see why it works, why it doesn't work, we do it this way. Notice that absolute of x to the fourth minus 4y squared over x squared plus 2y squared. Okay, if I say that the y equals to 0, okay, notice that x squared plus 2y squared is always greater or equals to x squared, is it right? Why? Because 2y squared is non-negative, right? And for that reason, if I do the reciprocal, then 1 over x squared must be greater. Okay, I hope this explains something. Okay, now then, because of this, then I can squeeze this from above using x to the fourth minus 4y squared over x squared, right? Okay, but this one, you will see that this will eventually squeeze down to 0 as x and y going to 0. Okay, yeah. I think I want to say, and let me be a bit careful there. This is actually bounded above by x to the fourth over x squared plus 4y squared over x squared. Okay, now I know this if this is equal to x squared, right? Okay, plus 4y squared over x squared. But when x goes to 0, this goes to 0. But when x goes to 0, it depends on the y's there. X and y goes to 0, but this will go to 4 when y equals to x. You see that? Okay. In other words, if I set the x equals to y, it may not work. We try to squeeze it. When x equals to y, it doesn't work. Let's say the x to the fourth minus 4x squared over x squared plus 2x squared. That will give us x squared minus 4 over x squared times 3, right? You will see x squared minus 4 over 3. Now when this goes to 0, then we get the limit negative 4/3. Okay, so we found that we can use this y equals to x as our path. Now, apparently, here in my original work, I didn't use that path x equals to y. I just used x-axis, y-axis, and that already gave me different limits. Okay, but if you try to do the scratch work, and on the scratch work, when you try to squeeze that, you will see, hey, you know what? It doesn't work. You cannot squeeze that down to 0 along this path. Okay, if you set your x equals to y. Okay, but Thomas, how then you use different paths? Well, I simply know that my limit does not exist. Okay, the limit does not exist when x equals to y along this x equals to y path. But when I step back and I look at these limits, when I go using along x-axis and along y-axis, it turns out it already gives me different limits. So I use basically two simpler paths to show that the limit are different, therefore the limit of this function does not exist at 0, 0. Okay, so my key point is this. My key point is not like, okay, use these paths to show the limit does not exist. If we know the limit does not exist, then we try to show two different paths, and two simplest paths are x-axis and y-axis. Those are two simplest paths. Okay, in fact, I usually do that first, and if I use along x-axis, along y-axis, I get the same paths, the same limits, then I try to squeeze that. Okay? If the squeeze work means the limit exists, then therefore I show the formal work again that the limit exists. But if I try to do on my scratch paper, x-axis, y-axis give me the same path, then I try to squeeze that on my scratch paper again. When I try to squeeze it, it doesn't work. I see which path it doesn't work. Okay, let's see the next question. For example, number 10. We have 5y to the 4th cosine y squared. Number 10. Limit as xy going to 0, 0 of 5y to the 4th cosine squared x over x to the 4th, y to the 4th, x to the 4th plus y to the 4th. Let's see, if I go along x-axis, I'll show you my scratch work again. I know the answer already. It's not about that. It's about me teaching you, right? So be patient with me if you already know the answer. So if I go along x-axis, means the y equals to 0, right? So I will get 0 cosine squared x over x to the 4th plus 0 to the 4th. Under condition of limit, right? This is equals to 0 over x to the 4th, which is equals to 0. So the limit as x going to 0 is 0. This is just my scratch work, so I don't worry about proper notation. If I go along y-axis, then I set my x equals to 0, right? But cosine 0 is 1, right? So 5y to the fourth over y to the fourth. That's y. So as y goes to 0, the limit is still 5. Oh, okay. So we now get two different limits, two different paths that give us two different limits. Okay. Then I move this work to my formal work along x-axis, which means I set my y equals to 0 and my x goes to 0. Okay, limit xy going to 0, 0 of 5y to the fourth cosine squared x over x to the fourth plus y to the fourth equals to limit x comma 0 going to 0, 0 of 0 to the fourth cosine squared x over x to the fourth plus 0 to the fourth, that is limit x going to 0 of 0 over x to the fourth, but you want to show that it is 0 on arrival, right? The limit of 0 before you plug in x equals to 0. Now, along y-axis, we have x set to be 0, but the y is approaching 0. So limit xy going to 0, 0 of 5y to the fourth cosine squared x over x to the fourth plus y to the fourth equals to limit 0 comma y going to 0, 0 of 5y to the fourth cosine squared 0 over 0 to the fourth plus y to the fourth. This is limit y going to 0 of 5y to the fourth, again because cosine 0 is 1, over y to the fourth, right? Okay, which then the y to the fourth cancel because y is approaching 0 but not 0 yet. That's why we need to write this limit condition. Okay, limit y approaching 0, 5 is 5. So because we have two different paths that gives us two different limits, then the limit does not exist. Okay, but I still require you to write this properly. Limit xy going to 0, 0 of 5y to the fourth cosine squared x over x to the fourth plus y to the fourth does not exist. Okay. So if you look back to my scratch work, my first step is to try two simple paths. Do they give me the same limits? Okay. Now suppose we use along x-axis, along y-axis, and they give us the same limit. It doesn't mean the limit exists. No. Okay. Because for us to say the limit exists, you need to approach that 0, 0 from every direction and from every path. It doesn't have to be a straight path like the one we have here. Okay, so two different paths with the same limit does not guarantee that the limit exists. Okay, so if I happen to use along x-axis and along y-axis and both give me the same limit, then I try to squeeze that. Okay, now you will see that when we try to squeeze that, it's just like this may not be politically correct, but I just say this. It's like one way to know if someone is faithful is put that person under temptation. Okay, so you try to squeeze this guy down. We know that cosine x squared, cosine squared x is always less than equals to 1. So this is safely bounded above by 5y to the fourth over x to the fourth plus y to the fourth, right? Okay, now this is bounded above by 5y to the fourth over y to the fourth. and also bounded above by 5y to the fourth over x to the fourth, right? Now this actually goes to 5, equals to 5 under condition of limit, which converges to 5, okay? But this converges to 0 as y goes to 0. Okay, so from there you see that when I try to squeeze that, then it depends on which path I go along to give me different results. Okay, in other words, when I put this guy under temptation, I put this guy under pressure. When I try to squeeze this person, it turns out that he spits out two different answers. Depends on how I pressure this person. Okay. Of course, these two examples, number 9 and number 10, are not enough. Let's do more. In fact, toward the end of this section of these limit questions, I will show you another method, okay, which actually was explained in our text, in our exercise set. Okay, number 12, we see that the limit is not going to 0, 0, but going to 1, 0, but that's because 1, 0 is not in the domain, right? If you plug in 1, 0 directly, you will get 0 over 0. Okay, so how do we handle this? Yeah, don't worry too much. Let's see. So number 12, we do the scratch work. So xy minus y over x minus 1 squared plus y squared. This is y x minus 1 over x minus 1 plus squared plus y squared. This is under the situation of xy going to 1, 0, right? Which also the same to say that x minus 1 comma y approaching 0, 0. Is it right? Okay. In other words, now, if this is the limit under the condition of limit x, y going to 1, 0, I can play with that now and call that limit x minus 1, y going to 0, 0. Limit blah y going to 0, 0 of y blah over blah squared plus y squared. I basically kind of modified my work for now. Okay, and then from there I see, okay, then if I go along blah axis, which means my y is already set to 0, but my blah going to 0, then I will get 0 over blah squared plus 0 squared. That's 0, right? Approaching 0. But if I go along blah already 0, but y goes to 0, I will still get this. Do I get the same thing? Yes, I get the same thing, huh? I get the same thing, but does it mean the limit exists? Hold on, maybe not. Maybe not. Let's try to squeeze this. So y blah over blah squared plus y squared. This is less than equals to y blah over blah squared. I can cancel the blah, but then this will fail to converge to 0 as we expected. Okay, this will not go to 0 when y equals to x. I'm sorry, y equal to blah. In other words, if we go along this path here, okay, so how do we parameterize that? If our x equals to t, or maybe our y equals to t, then our x will be t plus 1, huh? Okay, let's try. So this take a lot of space, huh? Okay, the scratch work is a lot longer. Okay, so if I go t plus 1 comma t, if I go along this path, then xy minus y over x minus 1 squared plus y squared. If I replace the x by t plus 1 and the y by t, you'll get t squared over 2t squared. That's 1/2. Right? Under condition of limit, of course. Oh, now we get two different paths. Okay, so one of them we can use, the point that we are approaching is 1, 0, right? Okay, so we can say one way is to approach along x-axis maybe. When we go along x-axis, which means the y equals to 0, you will get a certain limit, right? But when we go along y equals to x minus 1 path, if I go along this path here, the limit will be different. Okay, in fact, if I go along the x path, the limit will be 0. If I go this way, the limit will be 0. But if I go along that y equals to x minus 1 path, the limit will be 1/2. Okay, now we get two different paths, right? Let's go back, now show the proper work. So number 12. So limit xy going to 1, 0 of xy minus y over x minus 1 squared plus y squared. So if I go along x-axis, notice that along x-axis, your x is approaching 1, but the y is already set to 0. Okay, so limit xy going to 1, 0 of xy minus y over x squared minus 1 squared plus y squared. I set the y equals to 0. So x times 0 minus 0 over x minus 1 squared plus 0 squared. That's limit x going to 1 of 0 over x minus 1 squared, which is already 0 even before we replace x by 1. However, when we go along y equals to x minus 1, which means I will parameterize it this way, t plus 1 comma t, okay, and as t goes to 0, 0, maybe I want to, this will go to 1, 0, that's the destination point that we are going to as t approaching 0, right? So limit xy going to 1, 0 of xy minus y over x minus 1 squared plus y squared. I will replace that t goes to 0, but then my x I replace by t plus 1, my y I replace by t. Okay, you will see on the top, this is limit t goes to 0 of t squared over 2t squared, which is limit t goes to 0 of 1/2 before I plug in t equals to 0. Using those, then we see that, so the limit as xy going to 1, 0 of xy minus y over x minus 1 squared plus y squared still does not exist. Okay, that's for number 12. How about number 14? I think number 14 is easy. Just do factoring, right? You do factorization on the top. Okay, you will see the limit goes to 0. Okay. Now, how about number 16? X squared sine squared y. Number 16. Number 16. Limit of xy going to 0, 0 of x squared sine squared y over what? X squared plus y. Is it right? X squared plus 2y squared. X squared plus 2y squared. If I go along x-axis, which means the y is 0, it is 0. If I go along y-axis, which means x equals to 0, the limit is still 0. Okay, let's try to squeeze it then. So you see, I actually start doing faster. I don't write down my scratch work anymore because those are the standard procedure, right? Okay, you try along x-axis, along y-axis to approach 0, 0. Okay, so let's try to squeeze it. X squared sine squared y over x squared plus 2y squared. This is less than equals to x squared over x squared plus 2y squared. But this guy is less than equals to x squared over x squared, which goes to 1. Oh. So in other words, if I go along x-axis, hold on, but if I go along x-axis, it will be 0 though, right? Okay, seems like it's approaching 1, but that we killed the guys that make it 0 first earlier. No, I don't think so. So let's try to squeeze it another way. So x squared over 2y squared. And if I set my x equals to y, that basically becomes x squared over 2x squared. That converges to 1/2. But if I set x equals to y, so t squared sine squared t over t squared plus 2t squared, that's t squared sine squared t over 3t squared, that's sine squared t over 3. That still goes to 0 as t goes to 0. So yeah, because the sine squared y actually get killed too early. And let's start all over. So far, I thought I have the path, right? I set x equals to y, but when I set x equals to y, I still get the limit goes to 0. Let's squeeze that another way. So instead of killing something at the bottom, let's kill something at the bottom first. So x squared plus 2y squared like this. This guy is, oh, you know what? We can squeeze it this way. So this is actually x squared sine squared y over x squared, which is less than equals to sine squared y, which goes to 0 as y goes to 0, right? Okay, so that's our answer. So okay. So we will show that absolute of x squared sine squared y over x squared plus 2y squared. This is less than equals to x squared sine squared y over x squared, which is less than equals to sine squared y. I can get rid of the absolute sign because sine squared y is positive anyway. But this actually goes to 0 as y goes to 0. Okay. But hold on, Thomas. You are saying that at some point the limit is 1. No. It's bounded above by 1 though. It's bounded above by 1. This guy is bounded above by 1. Doesn't mean it is 1, right? This guy is bounded above by 1/2. Doesn't mean it is 1/2. Okay, see, I tried to squeeze it and it fails at some, seems like it fails at some point, but when I use the path that I think where it fails, turns out that it still gives me the limit zeros, right? Okay, so in other words, try to squeeze them itself is not the only way to show that the limit does not exist or exists, okay. Here I squeeze it down to only say that it's bounded above by 1/2, right? But if I use that path that proposed from that earlier, I still get the limit equals to 0. Okay, but if you can bound it above by something that is convergent to 0, then this guy must be convergent to 0, right? Does it make sense? Okay. So now with that says, then so the limit of xy going to 0, 0 of x squared sine squared y over x squared plus 2y squared equals to 0. Now, at this point, you may wonder, so Thomas, you say that what we can do is we try to squeeze it, and if it fails, that we get the path. We may get the path, okay, but you test that path again, see if it works, right? If it doesn't work, then you look back and find another way to squeeze it, right? And here, another way to squeeze it turns out to be the way that we can squeeze it down to 0. Okay? So that's for number 16. Can we try number 15, Thomas? That looks ugly. Okay, why not? Number 15, x squared y e to the y. So number 15, limit xy going to 0, 0 of x squared y e to the y over x to the 4th plus y squared. Is it the question? X to the 4th plus 4y squared. Along x-axis it's 0, along y-axis it's 0. Let's see which way it will not work. X squared y e to the y over x to the 4th plus 4y squared. This is bounded above. This is bounded above by x squared y e to the y over x to the 4th. This is bounded above by y e to the y over x cubed. This is y here. I'm sorry, x squared. Now this will not be 0. And the e to the 0 is 0, right? Okay, so I don't worry about this for now. In other words, I can say this is y over x squared of e to the y, but this will not go to 0. This will fail to go to 0e to the y when y equals to x squared. In other words, when I try to approach using xy, when I use this path, this may not work. Okay, let's try. So replace x by t and y by t squared. That's t to the fourth e to the t squared over 5t to the fourth. This will go to e t squared over 5, which converges to 1/5 as t goes to 0. Okay. But we know along x-axis, along y-axis, we get the limit is 0, right? Okay, so we get the second path already. Okay, let's execute that. Let's execute that. So number 5 along x-axis, which means our y is set to be 0, but the x approaching 0 of that limit. It's equals to limit x0 going to 0, 0 of x squared times 0e to the 0 over x to the fourth plus 4 times 0 squared. That is already 0 on the numerator, right? So that's limit x going to 0 of 0, that's 0. However, if we go along the path t squared, and now of course you need to make sure that this actually approaching the coordinate that you want as t goes to 0. Okay, so we have limit xy going to 0, 0 of x squared ye to the y over x to the fourth plus 4y squared equals to limit t goes to 0 of t squared plus t squared times t squared times e to the t squared over t to the 4 plus 4t to the fourth. That is limit t goes to 0 of t to the fourth e to the t squared over 5t to the fourth. Now the t to the fourth cancel first before t is not 0 yet. Now then when I replace the t by 0, I get 1/5. Okay, so then from there we say, oh, okay, so the limit as xy going to 0, 0 of x squared ye to the y over x to the fourth plus 4y squared does not exist. Okay, now let's do more. We have number 17 and number 18 here. I actually want to go over number 17 because I think that's the first time we see something with radical, right? But in calculus 1, we saw this type of question though. If you are dealing with radical, if you plug in 0, 0, you will get 0 over 0 over 0, which is undefined. Oh, by the way, Thomas, can we use L'Hopital rule? The answer is not directly. You can only use L'Hopital rule once you have a single variable. Okay, in other words, like you have, once you have this case, then if you want to do L'Hopital rule, then you can. Okay, even though you can see there is not necessary, right? Okay, But if we have radicals, things like this, try to multiply by the conjugate first on the numerator and denominator in case something cancels. By the conjugate, I hope you understand what is conjugate. At this point, you are in Calc 3. So when I multiply by the conjugate, limit xy going to 0, 0 of x squared plus y squared times square root of x squared plus y squared plus 1 plus 1 over the denominator. When I multiply, I will get x squared plus y squared plus 1 minus 1, which is x squared plus y squared, right? And therefore I can cancel that x squared plus y squared on the numerator and denominator. I am left with the square root of x squared plus y squared plus 1 plus 1, which is equals to 1 plus 1, which is 2. So the limit here exists. Okay. Now, how about number 18? Number 18, I do the scratch work first. Scratch. So in your test, please don't show the scratch work. If you do, do it aside. Okay. So we try to squeeze this. I mean, along x-axis and along y-axis, the limit is 0. But what if there's another path that gives us something not 0? Let me bound this above by xy to the fourth over x squared. This is equals to y to the fourth over x. This will fail to go to 0. This will fail to go to 0. In fact, it will go to 1 along x equals to y to the fourth. It will go to 1, right? So let's parameterize that using xy equals to, if the y is t, and then the x will be t to the fourth. Now notice that this converges to 0, 0 as t goes to 0, right? Okay, I still need to test this though. Okay, so t to the fourth times t to the fourth over t to the fourth squared plus t to the eighth. That's t to the eighth over 2t to the eighth, which is 1/2. That converges to 1/2. Okay, so along x or y axis, it will be the limit is 0, but along this t to the 4 comma t, the limit is 1/2. Okay, let's picture that first. In other words, if I go along x-axis, the limit is 0. Along y-axis, the limit also 0. Okay, but when I go along x equals to y to the fourth, if I go along this path here, the limit is actually 1/2. Okay, now that's the scratch work, right? Now I'll show the formal work. The formal work, we say along x-axis. We know the answer is 0, but you still need to show the work, okay? You and I know when you go along x-axis, the limit is 0, but you still need to show the formal work properly. Thomas, that's time consuming. Trust me, for me too. If it is time consuming for you to write it, it is time consuming for me to write it, to read it. Okay? But how about just do what is right instead of doing the shortcut? Thomas, you and me understand each other. What I try to show, what I try to do, what I try to show. Don't you just try to understand? Well, the answer is no, I'm not supposed to do that, right? Okay, however friendly we are to each other, you and I still need to show the work properly. Okay, this is limit x going to 0, 0 over x squared that is limit x going to 0 of 0, which is 0. But when we go along t to the 4 comma t, which approaches 0 0 as t goes to 0, then we get limit xy going to 0 0 of xy to the 4th over x squared plus y to the 8th equals to limit t approaching 0. Now I replace the x by t to the 4th and the y by t. This is limit t goes to 0 of t to the 8th over 2t to the 8th, which is limit t goes to 0 of 1/2, that's 1/2. So let me give more space. So limit xy going to 0 0 of xy to the 4th over x squared plus y to the 8th does not exist. Okay, so that's for number 18. More. In this number 20 here, we have more questions though, a lot more. Okay, be patient with me. You can pause this video, of course, if you need a rest. Now, number 20, this is the first time we see the limit of a function whose domain is three-dimensional space, except the origin. Okay, so the domain here is R3, except the origin. Okay, the way we do this, we will apply similar idea. Okay, we will apply the similar idea. So on the right hand side here, I will try to squeeze it, xy plus yc over x squared plus y squared plus c squared. Let's say the x equals to 0. For x already equals to 0, then we will get yc over y squared plus c squared. Now, I hope at this point you get used to this. You know that this one, the limit does not exist. The limit is 0 along y-axis and along z-axis, but it will be 1/2 when y equals to z. Okay? If you don't believe me, you try to squeeze it, then you will see that's what happened. Okay, in other words, we actually already find a path. We already find a path 0 t comma t. When we go along this, right, you will see 0 t t, that's 0 times t plus t times t over 0 squared plus t squared plus t squared. This is t squared over 2t squared, which is 1/2 converges to 1/2. But if we go along x-axis, that will be 0 plus 0 over x squared plus 0 plus 0, which is 0 over x squared. That's 0 on arrival. Okay. So you see that we still applied our squeezing, and right now we get two different paths, one of them along x-axis, that gives us limit 0, and another path that gives us limit different from 0. So formal work along x-axis, which means I set the y equals to c equals to 0, and x is approaching 0. Okay, so limit x, y, z going to 0, 0, 0 of that xy plus yc over x squared plus y squared plus c squared equals to limit of x 0, 0 going to 0, 0, 0 of x times 0 plus 0 times 0 over x squared plus 0 squared plus 0 squared. That's limit x approaching 0 of 0 over x squared. That's limit x approaching 0 of 0, that's 0. But when we go along 0t, which goes to 0, 0, 0 as t approaching 0, then limit x, y, z going to 0, 0, 0 of xy plus yc over x squared plus y squared plus z squared equals to limit t goes to 0 of 0 times t plus t times t over 0 squared plus t squared equals to limit t goes to 0 of t squared over 2t squared. We cancel the t squared because t is not 0 yet. We get 1/2. Then we send the t approaching 0. It is still 1/2. Okay, so limit of x, y, z going to 0, 0, 0 of xy plus yc over x squared plus y squared plus c squared does not exist. Number 24. I think at this point you start seeing this pattern already. Notice that you have x, y over x squared plus y squared. This actually converges to 1/2 along t comma t approaching 0, 0, right? Okay, it will be approaching 0 along x-axis. Okay, call this a node. Notice that in this number 24, they basically replace the y by y cubed, right? Okay, so let's modify that. If you replace the y, now becomes y cubed, okay, then let's modify the t becomes, for the x becomes t cubed. Okay, so let's see, along x-axis, maybe I go back to explain this. When you try to squeeze this, then you will see this is less than equals to xy cubed over x squared, which is y cubed over x, which is not convergent to 0. In fact, it is convergent to 1 when your x equals to y cubed. In other words, you can parameterize using this and see how it works. Okay, but we know along x-axis we have limit xy going to 0, 0 of xy cubed over x squared plus y to the 6. We set our y to be 0. Limit x going to 0 of 0 over x squared. That's already 0 before x is replaced by 0. Okay, however, when we go along t cubed comma t approaching 0, 0 as t goes to 0, and we get the limit to be something other than something other than 0. Okay, so limit xy going to 0, 0 of xy cubed over x squared plus y to the 6 equals to limit t goes to 0 of the x replaced by t cubed, the y replaced by t, over t cubed squared plus t to the 6. That's limit t goes to 0 of t to the 6 over 2t to the 6, which is, I cancel the t's because the t is not 0 yet. I get 1/2. So the limit as xy going to 0, 0 of xy cubed over x squared plus y to the 6 does not exist. Okay. Number 29 to 38, determine the set of points at which the function is continuous. The hint is a function f, x, y, or including z, is continuous on its domain. We actually learned that in Calc 1. Okay, so number 30, for example, the domain is xy, where 1 plus x minus y must be non-negative, right? So we will have negative x plus y is less than equals to 1. Or maybe we write it this way. So 1x plus 1 is greater equals to y. So on the coordinate planes, x plus y equal x plus 1 equals to y is this line here. Okay, and the y is less than that. Okay, because that's the domain, then it is also continuous there. So continuous on xy, where y is less than equals to x plus 1. Okay, number 32. Number 32, it's continuous everywhere except when e to the xy equals to 1. So that's continuous on all coordinates xy where e to the xy is not equals to 1, right? But e to the xy is not equals to 1 if and only if xy is not equals to 0, which means x not equals to 0, y is not equals to 0. Okay, so it is continuous on xy beside the x-axis and y-axis. Beside, not including. Okay, if you try to sketch that, it's everything except this. So the red one is the one I exclude. Okay, everything else is okay, except the x-axis and the y-axis. Okay. How about number 33? That seems to be interesting question. Yeah, how about number 33? Number 33 is natural log, right? So the domain is all xy where x squared plus y squared minus 4 must be strictly positive. In other words, x squared plus y squared has to be greater than 4. Okay, that's where it is continuous. So it is outside of this of radius 2. Outside of that, this of radius 2. Not including the boundary, though. The boundary still does not make us continuous there. Okay, now number 37 and 38, are they continuous? Okay, number 37, I do number 37 first. So let's review a bit. Okay, let's review a bit so that then you will see why we do things that way. Okay, that the function f(x,y) is continuous on coordinate, let's say AB, at AB, if first the limit exists. Second, A comma B is in the domain. And because it is in the domain, then FAB is well defined and equals to the limit. Okay, so for number 37 and 38, you will see the way I show the work to see if it is continuous at 0, 0 is basically doing as follows. For number 37, I want to show that limit, so step 1, limit of xy going to 0, 0 but not 0, 0 of x squared y cubed over 2x squared plus y squared, that is bounded below by limit xy going to 0, 0 of x squared y cubed over y squared, right? Which is less than equals to limit xy going to 0, 0. Well, actually not less than equals to, is exactly equal to, sorry. Absolute of x squared y, but this goes to 0 as xy going to 0, 0. Okay, so the limit exists. So the limit of xy going to 0, 0 of x squared y cubed over 2x squared plus y squared equals to 0. Okay, unfortunately, step 2, f(0, 0) is 1, which is not equals to the limit. Okay, so fxy, which is not equals to the limit. So the limit exists and xy is in the domain. I mean 0, 0 is in the domain. but because they are not equal, it is not continuous. Is not continuous at 0, 0. In Calc 1, we call this jump discontinuity. Right? It's like this. You can imagine like we have these two. The function is just undefined at that one coordinate 0, 0. Okay, but then when they try to fix it, they try to patch the hole. They patch it at different y. Okay, so they have a jump discontinuity. No, I'm sorry. This is not the jump discontinuity. It's just you patch the hole in a wrong value. So it's still discontinuity. Jump discontinuity is like if you have this, something like that. I think I forgot. I think I'm thinking way too hard. Now, yeah, that's for number 37. Let's see number 38. Let's see number 38. You will see the limit does not exist though. Number 38. Okay. Step 1. Like when we try to do the limit, you will see along x-axis. Okay. You fill in the gap. Okay, you do it. You will get that's equals to 0. Along y-axis also, but if you go along x equals to y, at which basically you are saying that you use t comma t to be the path going to 0, 0. You will see the limit is 1/3. Okay, so it doesn't even have the limit. The limit does not exist. Therefore, it is not continuous. Okay, so xy over x squared plus xy plus y squared does not exist, and consequently that fxy is not continuous at 0, 0. Okay, so even the limit does not exist. That's number 38. Now, number 39 to 41, we are actually using a new technique in which we basically squeeze that using polar. Okay, we squeeze that using polar. So we replace xy, by r cosine theta, r sine theta. This goes to 0, 0. In polar, it will be r goes to 0 positive. The radius goes to 0 positive for every theta. And that's the key, for every theta. Okay? So, for example, number 40, we have limit xy going to 0, 0 of x squared plus y squared natural log of x squared plus y squared. That is equals to limit r going to 0 positive. Remember, we use r going to 0 from the right hand side because we implies that we squeeze that with positive r. Okay, you squeeze that from using positive r. Basically, you use a circle that you squeeze this circle with radius r down to radius 0. Okay, so we'll get r squared natural log of r squared, but don't forget for all theta. That's actually one of the key though. That's actually one of the key. This is equals to, oh, you know what? It seems like I need to use L'Hopital rule, but I can only use L'Hopital rule for single variable. And that's why this becomes handy. L'Hopital rule. Two over r. This is limit for r going to 0 positive for all theta. 2 over r squared, that is infinity. Oh. Is it right? Oh, I think, sorry. I make a mistake. This is supposed to be 1 over r squared. So the derivative will be negative 2 over r cubed. No, I was expecting this to be 0 though. So this is negative r squared, which is 0. Okay. Now, this works very well, especially if we have x squared, y squared. Now, let's apply this to number 39. Number 39, so the limit xy going to 0, 0 of x cubed plus y cubed over x squared plus y squared. This is limit of r going to 0 from the right hand side for all theta of r cubed cosine cube theta plus r cubed sine cube theta over r squared. Notice that I can factor the r squared from r cubed from the top, and you will see I can cancel the r squared later on. Because r is not 0 yet, right? This is equals to r times cosine cube theta plus sine cube theta. This is convergent to 0. Okay, because this may give you some constant, right? But as long as r goes down to 0, then the limit of the whole thing is 0. Okay. That's basically it, huh? Now, I want to show you that this, when you try to use this technique here for example, this one. For example, if I try to use limit xy going to 0, 0 of xy over x squared plus y squared. Now we know the limit does not exist because along x-axis is 0, but along x equals to y, it's 1/2, right? But suppose you notice that if we try to use polar, you will get r squared cosine theta sine theta over r squared. R goes to 0 positive for all theta. This is cosine theta sine theta, and there's no r as a factor that brings it down to 0. In other words, the limit for this does not exist because different theta give you different result, right? Okay. Now, more thing to say. One of the question we had earlier was three-dimensional domain, like which one? Like this one here, number 20. We can use a spherical coordinate system for this. Okay, so for number 20, we attack that number 20, we attack that another way. Limit x, y, z going to 0, 0, 0 of xy plus yz over x squared plus y squared plus z squared. Now the thing is, we have this question in order addition in which they did teach us to use a spherical coordinate system. Basically, we use this is equals to limit rho going to 0 positive for all theta and all phi. Okay, now the x then becomes rho sine phi cosine theta times rho sine phi sine theta, that's for the x and times y, plus rho sine phi sine theta times rho cosine phi over rho squared. Now notice that the numerator, we can factor the rho square out, and in the next step, as we expect, we can cancel the rho square. Sine phi cosine theta sine square phi cosine theta sine theta plus sine phi, sorry, this should be sine cosine phi here, cosine phi sine theta over rho square, right? But the rho square cancels, and we are left with sine squared phi cosine theta sine theta plus sine phi cosine phi sine theta, which give us different results for different theta and phi. Okay, so these were the last number 20 here, the way that I approached that using spherical coordinates. Was not taught in our textbook explicitly, because notice, remember, I said that the cylindrical and spherical coordinate system sections that I teach you in 12.7 suddenly disappear in newer edition. So of course, then they cannot teach this method anymore, right? But since we learned that in addition to what we learned from our textbook, then we can use this method already. Okay, that's for